So now let's look at how we can work out the shape function for a rectangular finite element. So as shown here, we have a rectangular finite element set up in this global coordinate x and y, where we have four nodes A, B, 1, 1, 2, 3, and 4, right? And to simplify things a bit, we also have the length of the elements A and the width B. Okay. Now, if we recall the definition of the shape function, typically what we want to do is we know the displacement at each of these four nodes 1, 2, 3, and 4, where we want to work out how to extrapolate or in this case interpolate the displacement of an arbitrary point x and y inside this finite element from the displacement at this four nodal point. Okay. Now to simplify the math a little bit further, rather than work on the global frame x and y, what we can do is shift this frame to the position where no 1 is. So this point in the middle, x and y, can be given in the coordinate in this x prime and y prime frame as s prime equal to x minus x1 and y prime equal to y minus y1. Okay, that simplified the math a little bit. And what we want to do, as before, is want to work out how can we work out the displacement of ux and uy, right? Based on the displacement at all the nodal points, or based on the coordinate x prime and y prime for this point. How to work out the displacement at arbitrary point based on its coordinates. And we can do that as what we did before. Say this is a linear function of x prime and y prime, so alpha 1 plus alpha 2 x prime plus alpha 3 y prime, right? That's what we did before. But because we have a rectangular matrix element that is able to deform, right, rather than just along the orthogonal direction, it can also deform along an non-orthogonal direction. For example, in this direction pointed with the red arrow, right? So when it does that, the x and y component will get mixed up together. And to take that into account, we will have a second order term here, which is the product of x prime and y prime. Okay, that's how we incorporate this kind of deformation inside. Okay, so here we have a second order term. Similarly, we can write the same equation for y, which is basically alpha 5 plus alpha 6 x prime plus alpha 7 y prime plus alpha 8 x prime y prime, right? So we have equation A and B. Now, because they are of an identical mathematical form, all we can do is basically focus on equation A, right? And as we shown for the triangular matrix element, what we want to do now is put in the displacement at the 4 nodes into the equation. So now what do we have? We have so it did this. My notepad is not responding correctly today. We have u1 x, u2 x, u3 x, u4 x. Now in this x prime and y prime frame, we know that for 1, we know that x1 prime equal to 0, y1 prime also equal to 0. That basically leaves us with alpha 1, right? For u2, we know that x2 prime equal to what? A, and y2 prime equal to 0. So that gives us alpha 1 plus a dot alpha 2. Okay, try to make this bigger. And similarly for u3, we have x3 prime equal to a, y3 prime equal to b. So we have alpha 1 plus a times alpha 2 plus b times alpha 3 plus, now we have this cross term a dot b dot alpha 4. And finally for u4, we have x4 prime equal to 0, y4 prime equal to b. So that leaves us with alpha 1 plus b dot alpha 3 equal to u4. Now what we need to do here is basically solve. Now what we need to do is to solve alpha 1, alpha 2, alpha 3, alpha 4, and put them back to equation A. So what's equation A? It's basically this guy here, right? How we get ux. Now, if we do that, I will strip all the derivation. We'll have u equal to, now I ignore the superscript x because x and y are related to each other by symmetry, so the equation for both x and y will look the same. So u, in this case, equal to 1 over a times b, a minus x prime times b minus y prime dot my Surface Pro is not responding brilliantly today. It's not quite brilliant, so let's try to work with it. Dot u1 x, oh, there's no x, dot u1 plus b plus x prime b minus y prime u2 plus x prime y prime dot u3 plus a minus x prime dot y prime dot u4. Okay, so this is our bring that back. So this is our interpolation function that allow us to work out the deformation of an arbitrary point inside a rectangular matrix element with respect to the displacement at each one of the nodal points. Okay, that's our interpolation function. Now we need to put that into a sort of matrix form because we know N is a matrix, right? Because we have 4 nodes, we know that the N matrix will be a 4 by 4 matrix. Furthermore, if you look at this equation here, there's no term that mix up U1 with other nodes, right? Each nodes are independent from each other. That means we'll only have diagonal matrix elements. That means N will look like N1, N2, N3, N4, where everything else is 0. Where N1, N2, N3, and N4 can be worked out from this equation here. What does that give? That basically gives me N1 equal to AB A minus X prime times B minus Y prime, which is this guy. Once you see that, you can straightforward work out what would other terms be. So N2 is 1 over AB X prime times B minus Y prime. N3 will be X prime times Y prime times 1 over AB. And 4 is basically 1 over AB A minus X prime times Y prime. So now we work out the whole shape function for a rectangular finite element. So far we look at how to work out the shape function for both triangular and rectangular finite elements. So in the last 2 videos for this course, we'll be looking at how to put everything together and work out the final stiffness matrix for this kind of these 2 kinds of finite elements.